क्या बोला था समझ आवाज नहीं हो रही तेज बहुत तेज हाँ
Hello, welcome back. They had some snack or no? Only tea. Was it from the mess?
हर पेपर
Yeah. Hello. Because these two folks were not there in the morning. Online. How do we know? Not counted. Okay. So, okay, so we discussed about underreporting, we discussed about certain data sets. Now, also, I was mentioning in the morning, when the data is very bad and you are in the middle of an outbreak, what data to use? So there is always other. We are now using satellite images, for example. We are using satellite images, which is easier to get in US. I don't know about here. But to give you an example, so this is a mortality data, and it is actually capturing burial sites. There are burial sites during COVID time. They were using Indonesia to capture underreporting. Yeah. So somewhere, even a person must die, they have to be somewhere, either buried under the ground or the burned, right? So those are the things that they were capturing to get a count of mortality. So you have to have some information from a real life, right, in order to model to capture the disease outbreak. And that's what is a very good example. So, for example, they record 3,000 burials a month in Indonesia in some cemeteries, and accounting for roughly, but their cases were not getting reported at all in that town. But that one cemetery was reporting 3,000 burials. So, also what we already know, if there is no outbreak with a major mortality, then there is a regular use of mortuaries, right? There are certain numbers of dead bodies come, which is on an average. They know. Every year they know. But if something increases beyond a traditional standard, then that is what is called as an excess mortality. The word excess mortality is used. And that is the data is assumed to be outbreak related, especially in COVID times. So that is what they were using to track case count. Okay, so you see, by hook and crook, you have to find some information that is real life information that you can use in the model. So excess at least 45. So excess means something which is beyond the standard that they were observing in that cemeteries before an outbreak. So they compare it the last year, for example. Okay, and then they map it out. So this is one of the studies that use something like that. Now there is something called as a real world data. Surveillance data also is part of it. The surveillance data that we talk about. But real world data consists of much more than that. So what is the real world data? Electronic medical records, which Sheetal will be talking about tomorrow also. So it comes from hospital setting. There is insurance claim. Why is insurance claim helpful in the disease? What does it give you? Health insurance. Health insurance we are talking about, right? Because what happens in health insurance? You buy some drugs, right? Or you go to the hospital for some checkup and you get reimbursed from the insurance, right? Now, not everyone is under insurance. I mean, many are, because government has a free insurance also, right? They track this. So that has cost of the services, medical services that you have taken, right? So it tracks infection, it's tracking the basically what drug you will not give it randomly, right? It will be for a specific disease. And therefore, the data is extracted from an health insurance also. But it's very difficult to get it. In US, there is companies that collect this data from private insurance companies by paying them. So these are primarily, these two data are, you have to pay money to get the access to that. It's not easily available. But this has a rich source of information about infections. That's what and mobility and mobile data. Mobile is a location-based services, that phone data that we were talking about. So where are these things helpful? Estimate the disease burden. It is used for estimating how many cases are occurring. It is also used for interventions, how badly or how good the interventions are doing. It is also do the cost effectiveness. So I remember I was telling you a drug which is costing $3.7 million, one dose, but it is cost effective. That means clinical benefit, that means you save the life of a person versus the cost of the drug. You balance that thing, it is how expensive that you can value your life. Does that make sense?
Yes.
So that's a cost effectiveness modeling that we do, where there is a model for the disease spread, then there is a model of intervention, and then there is a model of economics on top of it. So there's 3 layers of models interacting with each other. I think Shichand will be talking about at least 2 layers tomorrow's morning, basically. So interventions and disease. So you capture the disease, then you capture the interventions, then you capture the economics. There is another model on top of it, that is a behavior aspect or psychological aspects. That is because you see, people, somehow some drugs are easily accepted by the population. Some drugs are not accepted as easily, even though they have a good clinical impact, due to many variety of reasons, maybe cultural norms. People were not taking vaccine because their culture was not allowing it, for example, even though some vaccines have a greater impact. So there are lots of issues that comes, and then Shichand will also talk about social network, which is how people interact with each other and move around. And so that's a primer layer, then comes a disease layer, then comes an economic layer, then comes a behavior layer. And then there is on top of it, there is an evolutionary layer, which talks about evolution of strains. So depending on your research question, you mix and match many of these layers of the models. Okay. So anyway, so that's something. And how many of you know what is randomized data? What is randomized data? Have you heard of clinical trials?
Yes.
What is clinical trials?
With some drugs or something to different groups and analyze it,
Yeah.
whether it's
But why is that a real world data? No, it is not a real world data. Why? Because it is under constrained situation. It's in one hospital, people have to do certain way, they will get injection. In real world, you will not get a treatment sometimes, right? Real world is general situation, real world. So this data, which is not a clinical data, is referred as RWD. and any information that you extract from it is called as real world evidence. Okay, and these are all real world data that is we use in the modeling. Okay. So we use real world data to estimate. We already talked about it yesterday. Exponential growth, right? And then from there you calculate reproduction number. From there you calculate beta, and then basically you can capture the evidence. Okay, so yeah. So what are we using data for in the model? We are using data for calibration or fitting the model to get an inputs of the model. We are using data for validation. We are using data for doing sensitivity analysis. What data is different in sensitivity analysis? What data is different in sensitivity analysis as compared to these two data? The ranges, confidence interval, exactly. Right? Here you can find a point estimate and that is more than sufficient. Even in validation also. But probably for sensitivity analysis you need a range. Scenario analysis is also a different type of analysis. It tells you what if situation. What if I have infinite amount of dollars? You know, typically not. But you can run the worst case scenario, you can run the best case scenario, you can kill people in the model, right? So those are scenarios. Typically done for policy evaluation or intervention. Some of you are doing evaluation analysis in modeling from your research group project. The scenario analysis is must in that type of project. So SEIR model predict demand, how many cases will be there, that will help you allocate resources, how many doctors are needed, how many beds are needed. This is what the model. Mobility data will tell you how the policies are working or not working, right? You can compare with the prior to the implementing the policy mobility data and after implementing a mobility intervention, and you can compare. That will tell you the impact of that. Vaccination data is also used for strategy prioritizations. So these are the general things that that is helpful for you in the modeling. And I think that is all I have for this data. I hope it is gives you a picture of the way we use data in different ways, and what it is not that easy. When we need a data, we have to be very careful what we are asking for. We can't just say that we need a data, right? From someone. Okay, so I'll stop here. Thank you. So the next is, I think, Dr. So there will be next talk is instead of Ashwini, I think we are having Dr. Jayaprakash and he will be talking about some interesting stuff. The next speaker is Dr. Jayaprakash. He will come and I will introduce. But a brief introduction. Those two folks are they are mentors. Is Dr. Jayaprakash Tripathi, and he's a very hard-working professor I have seen. He has almost every year many PhD students sending to all around the globe. And you know, one is in Germany. You're based in Germany.
Yes, sir.
And you are in France. So one is Germany, one France, and I know very close. She is in one student. She is in Arizona, where I am actually, and there are other places I'm sure. So, are you guys still in touch with her, or
Yes, sir.
are you like I don't care?
No, which one? Last year, I accidentally met her in SAN conference.
Yeah, accidentally,
Yes.
not intentionally.
No, I didn't know she was coming there.
You see, he's contradicting himself. First he said, yes, I'm in contact. And then he's saying accidentally. Say it again? There you go. That's a good one. Accidental contact.
The participant is not there. Relax question. बोलते स्टैट वीडियो में डालना नेक्स्ट क्वेश्चन ऐसे लगे कि हाँ बच्चे इंटरेस्ट डूइंग टॉपिक नाम से ask questions.
Hello. Hello.
Yes, we can hear you.
Yes.
Can you?
Students are able to see.
There was network issue. Actually, I am getting proper place.
Okay. Maybe for a few minutes. So by the way, I was trying to have a panel discussion, so it was difficult. Yeah, audible, yes. Yes, can you hear?
Yes, sir. Actually, there was network issue in my room, so I was shifting my room.
Okay, fine.
Some problem in the.
Yeah, if you don't want to show us your luxury house, then that's okay.
Yes, sir. So I will share and just let me share my slide.
Yeah, and I will introduce you once you are ready.
Yes, sir. Yes, I'm trying to share the slide. Is it share, sir?
No, we don't. It's not.
I think screen might be coming, right?
Yes.
Yeah, I will open the slide.
Okay, so I was telling you about panel discussion. We were trying to get it today, but somehow we couldn't get the speakers. But tomorrow we will aim for tomorrow's morning. Okay.
Just give me sir 1 minute.
Okay.
Yeah, 1 minute. Yes, so now we can start.
Okay. Is it possible to see your face?
Yes, yes.
Yeah. And your luxury apartment? I want to see his apartment.
So, should I start now?
Yeah, so we will not be seeing your face.
I will try to
Okay, in
do
the
it, but
I'll
there might be
introduce
better
in the
problem.
meantime you whenever the internet is good you can have your
Sure, sure, sir.
okay, so it's pleasure and honor to have Dr. Jayaprakash Tripathi. He's as he's showing in his slide, he's a professor at Central University of Rajasthan. But personally, he's one very active person I have known actually. He has been, I think if I am not wrong, maybe 10 to 15, 20 projects he's running simultaneously. And many grants, he's writing books, he's publishing papers, and you can see the students there. So the output speaks more than what I can talk about him in words. And if you Google search, you will find his name in various works. We have been working for last many years, and our work has been published internationally in Royal Society and in American journals, for different journals. And so, and he has worked with faculties in Canada, and US, Europe. You know, okay, we can see you now. Can you hear us?
Yes, sir, yes.
And so you can see he has a beard also. Okay, he's not showing his apartment.
No, sir, yes, yes, sir. Thank you so much, sir, for such nice words. And so these slides actually I prepared in this night only because I was traveling from last 3-4 days, delivering some other talks on the Ramanujan Day.
Jayaprakash, if you can also give some brief background of yourself, what you have been doing, what work, and there are two culprits here sitting at the back from your group, from the research group. So you can talk a little bit about your background first, and then you can start with that.
Okay, sir. I do not have slide, but I will try to say something about it. Let me start finally thanking to this organizer of this GAM program, Global Initiative of Academic Networks, and this very fruitful workshop that people are enjoying and getting benefit from it. And I was personally very much interested to come also, and motivated the students that they go there, you will learn and get motivated for research on the topic data-driven thinking, modeling, and statistical inference for global health challenges. So, so personally, I thank to Professor Anuj Muvai sir and Dr. Tripathi for inviting me in this workshop and giving me chance to talk something about the disease models. First of all, as sir suggested that let me tell something about my research actually that we are doing. Still, I do not have any slide, but briefly, sir has told many things. But let me tell you. Actually, I will just start the things connected that those are connected in my research with Professor Muvai sir. I started interacting with him, if I recall, in 2016 or 17. Then we have started discussing some problem in disease modeling, particularly schistosomiasis problem, and then we also got some problem in COVID-19 human behavior modeling, particularly vaccine hesitancy problem. And also we have been publishing in some good journals like Royal Society, Open Science, Nonlinear Dynamics, and Mathematical Biosciences, Engineering, and some journal like that. But the most important thing is that I have been interacting with him and learning so many things in research, how to plan the research, how to do the research. Actually, these things are very important when you start doing the research, particularly in India, and outside the environment is something different. So it's my pleasure to be here, and also I am very much thankful to Professor Mugay sir and Dr. Tripathi to give me chance to talk here. And also, if you are interested to work in disease modeling, so you can contact our group, and we can have some discussion with you. And after having proper discussion and planning, then we can define the problem and we can work on it. So it's not like that immediately we start working, just finding some model and giving some results, mathematical and results, those kind of things. First of all, we have to plan properly, and we have to, as I have discussed a lot today, sir, that we have to have our objective actually on what problem means, what are the objective of the work that we want to do. So once objectives are clear, then only you can think about the method and about the model, which model you have to generate, or which model to develop, or which method you have to use. Without the objective, the problem is not clear, and you cannot jump into the solution or the developing the model. So the research objectives are very much important, and along with that, then only you will explore the background, right? Background behind the problem, and what other literature review and other things are there, and then you will come to your mathematical model, and then mathematical and numerical analysis and interpretation of results, and coming to the answering the research questions, because research is nothing but answering the research questions, objectives. So this is very important, that all the things I have learned from him during this last 10 years. So you can also Google if you are interested to see my work, and my work connected with the Professor Mugay and Dr. Tripathi, and then if you are interested, then we can discuss about that. So I think with this brief background, oral background, I am not having any slide, otherwise I can show you many things here. So we have also a lot of collaborative work.
आयु क्या कर रहे हो मुझे फोन करते
Hello.
Yeah. So I guess we got disconnected from the
Yes, sir. Automatically I was disconnected. I am
It's
guessing
fine.
the problem.
Yeah,
Yes,
it's
sir.
fine. You can switch
No,
off your.
no issue. I think, sir, now it is saved. Okay.
Yes, it is.
Yes. So by saying these words, we are all connected throughout the world, because there is networking, mobiles, and online. You can chat, you can message, you can email. Then we can discuss about the research work if you feel comfortable about that. So as I told you that I have prepared these slides, there might be some typo mistakes also, but I will try to rectify those as I will go ahead, because throughout the night I prepared and in the morning also. So I will basically talk about the you see, when you talk about the disease models, so what is the most important thing? Disease models, when you talk about, then at the same time mathematical, particularly mathematical model, then actually it is dynamic in nature. Derivative of the different compartments that I think you might have learned about small things, definitions, compartments, and different kind of rate of change of those compartments. So you get the derivative of those compartments, because the population from one compartment moves to the other compartment, so rate of change is there, and rate of change is there, so derivative you have in the left hand side. But what is the most important thing that actually changes the scenario in the dynamical analysis of the model, or you say prediction of the infectious people, or whatever you say about the model? What is the most important thing that is actually important is the interaction between the compartments. How the different compartments interact. In the you can understand a similar pattern as we do in the species model, right? In the ecology. So similarly, one and two compartments, suppose one is susceptible, other is infected, other is recovered. Then how these interactions are there? that decides what kind of dynamics and what kind of fitting and predictions and simulation results you will get. So that should be understood properly because we are going to model a particular kind of disease, and also it changes as the disease changes. For the different kind of diseases, you have the different kind of infection between the compartments, and hence to the infection function that you model changes accordingly. So we are going to focus on that. So I have written the title like non-linearity in disease models. So this non-linearity comes by easy to complex, right? When we start with the linear infection term, and then we go ahead slowly and we enter into the linearity and then the highly non-linear infection terms between the compartments. I think I am able. You are listening me properly? Yes, sir. Please, just can you answer me once?
Yeah, we can hear you.
Yes, sir. Okay. So, I have tried to divide my talk. There might not be some proper sequence. So, let us come to the slide. Firstly, actually, I will just brief you in the first slide that how this non-linear means. There are different kinds of mathematical models. Like one is the mathematical model. These mathematical models are just a part of the mathematical model. Mathematical model is like C is that we have a different type of branches like disease modeling. This is mathematical model. Then we will come to the epidemic model and we will talk about particularly incidence, that the non-linearity will come in this incidence. Then the linear to separation, the simple non-linearity, the first simpler non-linearity. Then we will come to the other non-linear incidence rates, and then I will talk some crucial questions. Actually, those I have been thinking to just discuss with you in disease modeling. Some simple questions are there. So those are very important when you discuss somewhere that when we are getting such kind of scenario like constant recruitment, constant population, standard incidence, all those things. So models are basically two types. There are different types according to the nature of the models, but here we are talking about the linearity and non-linearity. So accordingly we have got two kinds of model. I have just taken the example from our disease model, but there are different kinds of examples we can take for the linear non-linear model. So you see the first model, di over dt equal to beta I. So it depends on I is our dependent variable. So it depends on I linearly, so it is called linear model. So how we define the linearity? Linearity is defined by the right hand side function. The interaction between the dependent variable that you take mathematically. Don't think about the infectious operation, but the I is the dependent variable. If we are not having the non-linearity in I, or if you are having more than one variable, dependent variables, and you are not having the non-linearity in the dependent variable, then the model will be called linear. So what do you mean by the non-linearity in dependent variable? Means simply there is not product of these dependent variables, higher power of dependent variables, and those functions will not come like transcendental. They should not be the argument of the transcendental functions. Okay, but those functions we are not going to include like time, cost, and exponential. So non-linearity comes in this way in the simplified form. But then when you try to define the linearity and non-linearity with the help of the more rigorous mathematical term, then we have to go for the linear operator, and you have to apply the linear operator here. If the function follows the linearity, then it is linear, otherwise it is non-linear. So it's a matter actually of discussion. We can discuss about this in some slides, but here we are not going to into that deep. So linearity means simple. The function in the right hand side should be linear in the dependent variable. That's it. Okay. Those dependent variables are what in your disease model? These compartments: susceptible, infected, and recovered. They are your dependent variables, right? In those variables, when they interact, then there should be linear terms in the right hand side. Like you see this point, di over dt equal to beta I in within bracket 1 minus I. So what we are taking here, growth depends on the interaction between variables, right? So it becomes non-linear. The I square is there. So this is the non-linear logistic growth rate, and this is the linear growth rate. Okay. And similarly, as I told you that depending on the nature of the classification, we have the different kind of mathematical model, static dynamic model, and then again, depending on the time that you are taking or the scenario that you are modeling, if the discrete time is important there, time is in the discrete steps like days, weeks, hours, then we will get a discrete model. Here, one example is there. And if the time is continuous, then you can have a model like SIR model, SIR model, SIS model, and other models like that. So let us don't go into that deep. Actually, otherwise we will move to the mathematical modeling part. So why actually epidemic model? I hope that you have been discussed, but I will just tell very briefly. Epidemic model is mathematical or computational framework, right? So when you are talking about epidemic model, then it is not required that you always develop the mathematical. That might be the computational work also. You have data that you can compute, you can estimate the parameters, and you can predict the scenarios. You can go for the simulation of the thing. So why we do this? To describe spread of an infectious disease, because we are trying to learn what kind of dynamics is there or what is the future prediction there, right? How many infectious person will be in coming days. So and you want to explain the scenario also, and you want to tell something about the control strategy that you are going to apply, like intervention scheme, different kind of intervention schemes. So for those reasons actually we are going to have the epidemic model. And like very simple question I have written: how fast will a disease spread? When will the infection peak will come? So and how effective the intervention will be, like control strategy, vaccination, isolation, treatment, other things. So if you want to particularly answer these questions, or you can ask that will the disease will die out or persist for longer time? Somebody may be interested in the disease dynamics also. What kind of dynamics we are going to get? You want to predict the outbreak size and duration. So there are different kinds of, and if the disease is very kind of fatal, then these questions becomes more important. Like you have seen the COVID-19 in the recent days. So these are the questions, actually basic questions. Those are the questions of our research when we do, and ask the question becomes more precise when we do the research in a particular kind of disease. Then actually it becomes our research questions also. So here coming to the nonlinearity part, I have just table, but this table will come back again when we will go ahead. So here I have written the we are going to define the incidence rate. So these are the mathematical form of the incidence rate. You might be seeing some models that we have been discussed. I have written here the 5 kind of incidence rates. One by one we will come to this. But all the incidence rate, whatever you are taking here, they have some particular reason why you are taking such kind of incidence rate. But in the different kind of scenario, the different kind of incidence rate might be pretty well. Okay, so we'll come back to that. So I think, sir, SIR model has been discussed properly. Should I take that?
Yes. Yes. Yes, it has been.
Okay. So let me just take the important points. So rate of change of, yes, you see there are 3 compartments, SIR, and we have taken the population, and total population is constant. So DS over DT, you see, we have taken, what is the incidence here? The number of individuals who become infected per unit time in epidemiology is called incidence. So when the number of individuals those become infected per unit time, then they will come out from the S class, control class. So we are taking DS over DT is nothing but, and we are not including other kind of interactions or any kind of thing. So simply we are just taking the incidence term minus incidence, because they will get out from the susceptible class. So if I can get this incidence term, then immediately this first equation will be modeled. Okay. So the you see we take the CN is the number of contacts per unit of time this infection individual makes. So here we assume that the number of contacts made by one infectious individual is proportional to the population size with per capita contact rate scheme. So it is CN, right? So S by N is the probability factor, that is the probability that the contact is with susceptible individual. So if S by N is the probability that one susceptible individual have the contact. So if I multiply with the Cn, the number of contacts per unit of time the infectious individual makes, then we will have the number of contacts with the susceptible individual that one infectious individual makes per unit time. And if we take that successful contact, right, that convert into the transmission, the probability is P, then immediately this PCS is the number of susceptible individuals who become infected per unit of time per infectious individual. And if we take this PC equal to beta, that we call the transmission rate, and the beta SI is the number of individuals who become infected per unit time. And from this beta SI, if I take this, just you take the per susceptible individual, what is the infection rate? That is beta I, that we call the force of infection term. And this beta I actually, this lambda t actually changes that per susceptible individual infection rate, or you can say what is the infection risk, right, by a particular infectious individual, that is called the your in unit time, that is called your course of infection. This lambda t actually is responsible for the different kind of nonlinearity. As we will see this, when we change this lambda t, then we have the different kind of nonlinear incidence rates, because when we multiply this lambda t by s, then immediately we have the incidence rate. So lambda t is called the course of infection, and beta, the coefficient beta is the constant of proportionality, that is the transmission rate coefficient. So so the first term is model, right? Once you have the incidence, the ds would be equal to minus beta si, and similarly we will go to the second term, because from the infectious compartment the people are also getting out. So if we take that those individuals who recover or die leave the infected class at constant per capita probability per unit of time, that is alpha. So alpha I will be what? If I multiply this alpha with the total infectious individual, then it will give the number of infected individuals per unit of time to recover. So they will go to the other class, right? Recovered class R. So we will have the DIOD equal to beta Si minus alpha I, and then this alpha I will go into the recovered class. There are particular kind of assumptions, right, that we are taking. So we are getting this kind of model. So these are the three equations. I hope that you have been discussed this. So what is the linear here that we have to see? There are also two important things when you are going to model. So let me ask you a question. Somebody of you can answer. Why the initial condition in an epidemic model? Anybody of you? Why we take the initial condition? Very simple question. You can connect with your differential equation with this, right?
So why do we have an initial condition to the differential?
Yeah, anybody can answer this, then we can go ahead without answering this.
So the response is that we are doing time dependent analysis.
Sir, to like
Okay.
we are having system of differential equation. So
Yes.
initial value problem, this is the kind of initial value problem we supposed to transform that study in IUT form.
Yes. So this is initial problem is correct, but you are taking the initial condition, right? Initial condition, and with this initial condition, we want to start, right? Some population should be there at the initial level, and then you want to predict you want to know the future outcome. Okay, and with this also you also become interested that when the solution starts with this condition, then it should follow a path, a single path. Otherwise you will be in trouble, right? If you are taking the different kind of path. So actually with this initial condition and the differential equation, we become interested. Mathematically we want to see the uniqueness of solution, right? So that we have the unique kind of prediction. Otherwise if you have the 10 prediction, then you will be in trouble. Okay, so we can combine this initial condition, differential equation, and then the uniqueness of the solution. And when we formulate a model, why we need to be concerned with the unit of the quantities involved, right? Here you see, we do the dimensional analysis, right? The system should be dimensionally homogeneous. Otherwise, the system will be impaired. This is the one way how we can at least know that in the left, what is in the left, that is in the right. Both the unit of both the quantities, the left and right are same. So your system is dimensionally homogeneous or dimensionally correct. We have to see that, and in this model that we have developed here, actually this is happening if you will see. Okay, so in the left hand side, what is the from the first equation we what we see, what is the this left hand side, ds over dt or a over dt or dr over dt. So per unit time, number per unit time is what? This is the unit of the left hand side, and when you go see the unit of every term in the right hand side. See right hand side per unit term, why I say, because the second equation there are two terms. So the unit should be number per unit time. Okay, so that will come. You can analyze this, right? So beta must be 1 upon number of people, unit of time. So unit of the first term is the per unit time, and similarly the other term also has a per unit time. So number has no unit, right? Number is some number, so you can relate that. So the left hand side and the right hand side both have the unit per unit time, 1 upon unit of time. So it's okay. That is okay. Similarly, what is the message from here? You can at least, whenever you are trying to model some new problem, then you should have these ideas that whether my equation is dimensionally correct or not. It's not like this. In the left hand side you are having the hearts, in the right hand side you are having the right hand. Then the equation will be incorrect. At least our equation should be correct. Then only we have to talk about the computation and estimation and mathematical analysis. So these are the some things that we have to be careful about that. So now coming to the linear to non-linear. So this is actually HSI is linear incidence. Why we call it linear incidence? Because whenever you take the force of inflection, then this is what? Beta I, right? So it is linearly changing with I. When I change I, then beta I change is the sum multiple, constant multiple beta with I. So it's a linear graph, right? Beta I, force of inflection. So it is called linear incidence. So but there is some problem, right? So whenever some new incidence term will come, that means some other incidence terms, those are already available, they have some issues. So what is the issue here? If I take the I tends to infinity, then incidence tends to infinity, this is unrealistic. Inflection starts, this is okay. But when you say that it will go on and go on, when I increase it, then this is increased. But this does not happen. As you know, that there are different kind of interventions, limitations are there to actually restrict this infinite growth, right? So we have to just be very careful, and mathematically actually it is shown here. You see, if I take initially the population S is S naught, because for the initial time, for the shorter time duration, starting time duration, then you will replace this S by S naught, and you will get IT as this exponential growth if beta is not greater than alpha. Then it will actually go and explode. But actually this does not happen with the real academic data also. That do not follow the pure exponential for a long time, because people change behavior, intervention happens, and contracts saturate. So that means we need some other kind of incidence rate, because it will not work for the longer duration. For the shorter duration disease, it is okay. Okay. So linear incidence often, this is overestimating the new cases as we have seen, right? What is the overestimation here? See, this is overestimating the cases. For the shorter duration is okay, but for the longer duration is going to introduce overestimating. Unless intervention effects are absorbed into parameters. So non-linear form, what should be the non-linear form of this? How the non-linear will come? What was the force of inflection term? Force of inflection term was the beta I. So we have to modify this beta I here. Okay. So beta I, how you will modify? So the idea comes in mind that when the I increases after a certain time, then this lambda t should decrease. Okay. So in that, with that idea actually, this beta I is divided by another term 1 upon 1 plus alpha I, and this alpha is actually shows the saturation term, right? That saturate the incidence rate, this forcing term. So lambda t that was beta I, it is multiplied by 1 upon 1 plus alpha I, and now your forcing term is beta I1 plus alpha I. So when you multiply this by the susceptible, most susceptible individuals, then FSI equal to beta SI upon 1 plus alpha I becomes the incidence rate. And in that sense, because lambda t is beta I upon 1 plus alpha I, this is non-linear, then we say that our incidence rate in that model becomes non-linear. Okay? Go ahead. So this was the non-linear incidence rate. We will come back to all these things again. So another one is the standard incidence rate. So can somebody answer why we actually take the standard incidence rate in place of this linear incidence rate? One we have discussed, right? Non-linear situation kind of incidence rate. Standard incidence rate.
Anyone has an idea?
Yes, there are so different kind of regions, right? 3-4 regions, but one region at least somebody of you can tell.
Anyone has an idea? I think I heard many people doing epidemic models.
Yes, sir.
No, I'm not.
Yes.
Well,
Can you see?
Yeah, I don't think they have any answers are here from the audience, so go ahead.
Yes, we will come to the answer. Actually, let first we model it. So you see, it's not like that every time that everybody will infect to everybody, right? The infectious person. So there are diseases; those are particularly prevalent in the childs, but they are not prevalent in the older people. So and also there are some kind of restrictions also that a particular individual can infect the fixed number of contacts per time. So if the scenario is like that, then in that case, and also there are some other reasons also. In that case, you have to follow the modeling of the incidence rate, standard incidence rate in your model, beta SI by n, and how it comes. This is the standard for human diseases, because this actually happens if you talk about the wildlife diseases or the wild animals, right? The wild. So in that case, actually this will not be followed. But in the case of the human diseases, this case is very important that individuals are restricted, are somehow they have to infect a fixed number of contacts. Okay. So probability that a contact is with the infected person is I by n. So when we actually multiply with the total susceptible, if beta is the effective contact per unit time, beta s, then we will get what you have, beta s into I by n, and the final incidence rate is beta s I by n. Then your SIR model will be what? The term beta si will be replaced by beta si by n. Okay, beta si by n. And the model is with the standard incidence rate. So particularly you can say that the standard incidence rate models disease transmission by assuming E is a fixed number of contact per unit time. It's not like that everybody having the same number of contact, right? So we take the I by n, right? Then multiply with the all the susceptible individuals. So leading to an incidence proportional to a fraction of infected individual, that is I by n. Okay. So there is a other kind of scenario by which we can have the non-linearity into the incidence curve. So actually, when you see the modeling of these non-linear incidence rate, then actually by the different ways or different names, you can tell. So one term I have just got here, I have taken here, this is a fear, right? Psychological effect. So it is also a part of human behavior. Human behavior are different kind of behavior that human shows when the disease outbreak takes place. One behavior is a fear effect, other is the vaccine hesitancy. Some people are they are keen to take the vaccine, but some restrict themselves to take the vaccine. So vaccine hesitancy is another human behavior. So we are just talking about fear effect. So here, as you see, that it will decrease this incidence rate, right? Because once you have fear, then you are not going to interact with the people who, if you know that this person has a disease, you will avoid the risk of having the infection. So one general idea comes in mind that it will actually reduce this incidence rate, right? So the fear, as the fear disease, people avoid contacts, isolate vulnerability, wear mask, reduce mobility. So what is the result after that? Effective transmission rate decreases as infection increases. Okay, so that means we have to model a function into the transmission rate so that the transmission rate decreases and I increases, the infection increases. That is the idea, general idea. So we have to get that kind of function. So why fear must be included in the incidence rate? Because again, this is the problem, right? As we have modeled different kind of incidence rate. Similarly, this is your classical incidence rate, beta SI. So in this, again, it will go to infinity as I tells infinity, predicts unchecked exponential growth, predicts, okay, growth slows even before immunity dominates, growth slows even, it is repeated, I told you that this slide is not rectified, so now it is rectified, okay. Okay, so as I told you that transmission rate will decrease, so FSI, that was beta SI, it should be multiplied by a function GI that has certain kind of property so that this total FSI is decreased. How we will do this? So you have to think about the property of GI. So once you say that beta SI should decrease, then the GI should take value between greater than 0, less than or equal to 1. Otherwise, how you will tell that this will decrease? So whenever it will be 1, then this is your the linear incidence, cluster incidence rate. So this is the one condition. Other is its rate of change should decrease, right? dGi or dt should be less than 0 because it should decrease. Okay, then only it will decrease the beta SI. So saturation kind of incidence rate was beta SI upon 1 plus alpha I. This is again, there we have talked in some different way, but when the fear is moderate behavior can be compensated up to some level, then the effect of the fear can be modeled like this, and beta SI will be this term numerator, and GI, that is the fear term, will be 1 upon 1 plus alpha I will be multiplied by this. And I want to connect this one. If you are interested to work in disease ecology or the ecology, then you also see the fear there, right? Between the species. So the species that is eaten or consumed by other species, then that gets here, and due to that, as you are getting here the fear term in the incidence rate, in that way you get the reproduction get reduced because they are in fear, so they are not going for foraging outside properly. They are making them bound in a certain area to see that their growth rate get decreased. And in the first term, like growth rates, we have the function like this. So the idea is also collected from there. So here it is also collected here. But once the fear is high and situation are panic, then we take the also quadratic term, because here it just shows that if I increases, then this 1 upon 1 plus alpha I square decreases more fastly, because here you have the I square. So fear grows faster than infection. Yes, it will grow faster than infection because I is the infection and I square is the denominator. And similarly, if the situation is more panic driven response is there and very rapid behavioral suppression is there, then in that case you can model the fear with the exponential term. Okay, alpha I will be positive, so e equal minus alpha I will be this will be decreasing this beta SI, right? Beta SI. So there is a exponential fear function also. So actually what I want to tell you that, you see, in what way actually we are making in the linear incidence into the non-linear incidence. There are different ways by which you can model your function according to the disease, the scenario of the disease. So force of infection with the fear effect, we also generalize it. Lambda equal to FSI upon S. This is your force of infection, right? That you tell that risk per susceptible decreases as fear increases. That we have taken alpha I power P. So this power P, P can be between 0 and 1 if the fear is like moderate or like that, and if the fear is much higher, then you can take P greater than 1. So accordingly you have the different kind of non-linear terms model, the incidence function model by the non-linear terms. So actually we have to generalize this idea, and then accordingly we can understand the every kind of non-linearity. And here I have written some more non-linearity. One is this FSI, beta SI upon 1 plus alpha S plus gamma I, and this is more appropriate. This is called the mutual interference term, gamma I, and here this is widely used in eco-epidemics, right? And this is very much popular in the ecology, that is called predicted functional response there. So that kind of scenario also we take, and we also generalize it by taking the its generalization, that is called problematic incidence rate. I am not taking it here, but in this way actually we have the generalization of this non-linearity into the model and giving the proper reasoning of that. As here you see, I just taken a graph from this disease, this ecology. People are sitting there, they are going to ecology, my students. So, but when you take the I, right, I an infectious individual and I increases, then you, whatever the function you have taken, right, you see these functions, saturation kind of incidence rate, okay. This beta I upon 1 plus alpha I, okay. So when you try to plot this, then you have the saturation kind of incidence rate. You will have the plot like this, okay. So as the function changes, Bedingfield changes functional response, problematic functional response, incidence rate, or the heavy, the much fear is there, and the moderate fear is there, and the linear incidence is there, and this graph is there. So similar kind of actually what happens, this is not going to model when the infection is become higher and higher because things become saturated. Suppose infection is increasing and there are more infectious individuals, then the susceptible population will be very small. Then what is the idea behind that the infection should increase? It should saturate, right? At that time, then we have to model it by the, we have to capture this kind of scenario by the saturation kind of function. And here just I have taken a graph of the linear versus non-linear fitting. So you see this blue line, this is the COVID-19 data, the real data is there in between, and then the linear incidence fit is given by this red line, the red graph, and then this non-linear incidence is given by this graph. Right? So when you will see that which one is for a longer time, which one is going to be the more better, having the more better fit. So it will also depend on the disease, right? Which kind of disease you are going to take. If the disease is for a smaller duration, then the linear incidence may be better. But for the longer duration, you are seeing that it is much closer to this other matter, right? Real matter. So, sir, how much time we have now?
How much time do you need?
Sir, 5 to 7 minutes, 10 minutes.
You have 15 minutes.
15 minutes, okay. Okay, so I thought that you people, some of you might be new and some of might be aware about all these things that now I am going to talk about. So I just written some questions, right, that comes in our mind many times when we see the mathematical models of different kind of diseases, this compartmental model. So I have written here some questions. Let us just diagnose that why actually they are there. When can we assume constant total population in epidemic model? Anybody up? Yes.
Where there is no immigration or emigration.
Very good. There are so many reasons, right? It's one reason. Yes. So we are going to discuss in different ways, right? What are the ways how we can justify this assumption when we take in the modeling. Short time epidemics are there. Epidemic duration is short compared to human lifespan. Then actually we take the total population is constant. Epidemic duration is short compared to human lifespan, right? Short time epidemics. And as you told that natural births and deaths are negligible, immigration are negligible there. And for what disease actually it might be the useful sometime for influenza, that is for certain division, right? Season. And for COVID-19, short waves, not for the larger waves. Okay, measles outbreaks. So no demography included like SI, SIS, SIR, SCIR without mortality. We take disease does not cause death. Disease is what you want to say? Infection is non-fatal, not much fatal. Like common cold, some seasonal infection, as we can get influenza. Population is closed, as you told very correctly. No immigration or emigration is there. Population is isolated. If it is isolated, then no immigration, emigration will be there. So school, hostel, prison, hospital, what like this. Mathematical sense. Also, you see, it's not like that we are going to always compare with the real scenario. Sometimes we also we take this in consideration that total population of given model is constant for a mathematical simplification of mathematical factorability. By doing this, analytical study becomes easier. Stability, basic reproduction calculation, and bifurcation analysis, everything become much easier, right? Much simplified. So, but this is a mathematical angle. But if you want to the precise answer, then you have to see the what kind of disease you are modeling. That we have to take care. So, am I audible properly?
Yeah. Yeah, you are.
So, and then if you say that when we can take the total population is constant, then again the question comes in mind immediately that when we cannot take total population constant. So, just reverse everything, right? Whatever we have learned there. So disease induced death rate is there. Like if you have the COVID-19 severe waves, plague, Ebola, then we have to consider this. Long-term epidemics, endemic diseases are there. Because in the case of the long-term epidemics, then what you say that the infection duration is negligible in the period of the lifespan, it will not be considered there. So time scale is year or decades, worse and natural death matter there in that case, like tuberculosis, HIV/AIDS, malaria. Demographic effects are included there, and in that case, we have to not take the total population constant. Migration and mobility exist in that case. Like sometimes what happens that refugee movement is there, right? You cannot avoid that. Immigration and emigration is there. Urban-rural mixing is there. So in that case, you have to not take the population is constant, right? Method one or multi-population models are there. Age structure model are there. You are considering the age structure, then you have to make a different kind of groups, age groups, and we have to not take the total population is constant in that case. So the summary is that the total population can be assumed constant in an epidemic model only when demographic effects and disease-induced mortality are negligible over the epidemic time scale. This is very important. Epidemic time scale. Okay. Now next question is, why do we take the constant recruitment rate in some epidemic models? So again, if somebody of you can tell something, then we can go ahead.
Anyone has a response?
These are the very simple questions, right? But you should be prepared, right? When you are going for interview and for job and different places, then you have to answer these things.
So, sir, like in isolated place, it is a demography and a specific population. So there are natural causes of the birth and death. So it remains if there is no epidemic or intervention, then it remains at a constant value. So that's why we try to model initially like
Correct. So again there are different ways we can explain, right? I am not able to use here properly, but you might be very correct. So recruitment rate is what? Rate at which new susceptible individual enters into the population, right? Through birth or immigration. Anyway, they can enter into the population. This is recruitment rate, correct? So a constant recruitment rate means new individuals enter the population at a fixed rate. The rate is fixed for all the time, independent of current population size. It is not depending on the population size, right? So again, there are different reasons behind that why we take this. Mathematical simplicity or facility is one reason. What is the mathematical simplicity here? Mathematical simplicity is that you are easily able to prove the biological feasibility of the model, right? That boundedness and stability and everything. Stability is properly done. Indemnicity I think will be obtained in the model, right? When you take this constant recruitment rate. So in that case, these things are there. In the case of a mathematical simplicity, long-term disease model like tuberculosis, malaria, HIV, population size, stabilization, as I have already told you, immigration dominated populations, refugee camp and urban areas, birth are approximately constant per year in large population. Okay, for the large population, births are approximately constant per year. Mathematical advantage is the ethnic model that I already told you. So there, in the different angle, we can see this. Why we will take the recruitment rate constant in an academic model. So constant recruitment rate is used in academic models to represent a speedy inflow of susceptible individuals, particularly for long-term epidemic diseases. Long-term epidemic diseases while maintaining mathematical flexibility and constant population size. आपने देखा होगा कि जब आप ये नहीं लेते हैं constant recruitment rate, then you actually struggle while you are going to prove the population, bounded population size. In that case, mathematically, right? We have struggled in one or two this articles, okay? So when constant recruitment is not appropriate, in that case, when the population size was large, then it was appropriate. But when the short-term outbreak or a small population, then actually we have to be careful about that. Why and when mass action, density dependence, incidence rate, that already I have discussed, right? I think things was clear when we were trying to model SIR model, okay? So contact rate increases with population density. Beta SI means when I increases, beta SI increases. So more people, more contact per person. Typical in animal population or confined environments. Wildlife, bacteria in culture, insect populations. This kind of scenario is more prevalent, right? That gives you the exponential kind of postal curve. Okay. Small or fixed spatial area will be there, then you can model like this. No social structure or behavior change is there. Then you can go with this linear incidence rate. Okay, no limitation on contact, random mixing is there. But again, the same question comes that we have already discussed. In what scenario we should take the standard incidence? So each individual has a fixed number of contacts. In that case, large human population is there, like social network, limit interactions is there, because many times we have to have the social structure, right? The social structure is there. In that case, the interaction becomes limited. In that case, we have to take the beta s into I by n. So this is going to interact with the fraction of this index individuals. Variable population size is there, scaling by n, heat transmission, realistic. Long-term academic model is there, avoid unrealistically large infection. So again, just I want to tell you one work actually we have done with Professor in the collaboration of the Professor Movey sir. So many times what is happening that in the disease there is a heterogeneity, right? Heterogeneity can come in a different ways. There might be the geographical heterogeneity, there might be the heterogeneity due to your behavior, individual behavior. So it can come in different ways, right? So, like if you see the heterogeneity that comes via human behavior, then what kind of heterogeneity comes to the vaccine hesitancy that we have considered in this work? So, due to this vaccine hesitancy, we have to group the population. We have to divide the population into different groups. So, what we have done in that case, we have divided the population into two groups, right? One is H or resident population, other is NH or non-resident population. So, the model that you get is becomes the multi-group or two-group model. Okay? In that sense, actually, we have modeled this by considering the heterogeneity into the behavior. And we have actually done a very unique kind of model in this case. Actually, this model and this work becomes unique because no such kind of model people have presented in the case of the human behavior, hesitancy and heterogeneity. So this work actually we have done this. I am showing you the model. So there are, if you are interested, then we can discuss in detail, right? Every assumption is very clear. We have just given everything very properly, and how the transmission between the SH and SNH is there, SNH and INH is there, SNH, VNH is there, INH to RNH is there. So everything has been modeled with proper logic and reasoning. Okay.
Maybe we can, Jayaprakash, I think we
Yes.
can share the link of this paper with them and they can go over it, I think with the
Sure, sir.
on screen.
Yes, sir. I will share today. So about the references, they are not proper because they are the other references. But if you are interested, then I can provide you. You have to also know some good books. If you are going to start the research and you want to understand the modeling part and these kind of things that we are discussing here, then you have to read some good books in which these things have been introduced. Not like you are taking one paper and they have written some perspective, some objective. In that actually they might not be explaining all these things clearly. So you follow certain books, some good books, and then you, when you have some background, then you come to the model formulation and parameter estimation. Okay, thank you so much. I think I have.
Well, thank you, Dr. Jayaprakash. So, what was the gist of this talk actually? You can give me one-line answer. What was it trying to stress upon? So we presented. Let me backtrack the question. When we presented SIR model, what was the interesting part there? There was non-linearity.
So Suraj,
Yeah, you were saying something?
yes, sir, should I answer me? Should I answer? Or you want
I'm asking
to-
audience.
Okay, sir. Yes, sir. Yes,
So,
sir.
This is non-linear incidence.
non-linear, so beta SI, that's the only quadratic term.
Yeah.
Rest of the term were linear. If that term would not be there, it would be, we know the solution, exponential growth or exponential decline. We know. So the things becomes interesting by that non-linearity. And the other non-linearity that you put due to underreporting, due to various type of mechanisms. So his talk today was talking about mechanisms, the non-linearity choices. And he was linking it to the real life. That's the interesting part. And he was giving an example about fear, right? And it happens all the time in the disease setting. COVID, we were scared about like getting infection. And people did all sort of behaviors. So how do you capture these things? We are very weak in behavior models. This is one way to capture behavior aspects. So his work, he worked a lot like that. He's showing very simple these non-linearity terms, which is causing. And remember that outbreak, there are different types of disease count cases. It could be very simple, and then this is very peak, and then small, and then very high. You see some COVID data, for example, that is what it looks like. Simple transmission dynamics will not be able to capture that. And therefore you need this type of nonlinearity. But you have to understand what is causing that data to occur. It's a mechanism building. You are putting the drivers in the model to imitate the data that is observed in the field. Does that make sense?
Yes.
So his talk was very interesting. It's the heart of the problem. If we don't know how to capture what has happened in the past, history, then how will I predict it future? If I do a bad job in capturing how the curve look like, I will not get a good curve in the future, for sure. So this is something is what he was talking about, and he's calling it as a mechanism. And there are different mechanisms that you build in such models to capture it. So this is very interesting work, and he has done many high-level nonlinearity. He's showing some examples from it from a different research. Okay, so any questions on this to Dr. Tripathi?
So, 2 questions.
Louder so that he can see that. There is a question, Dr. Tripathi, for you.
The first question, share these references which you mentioned the book to study for the models. And second question is, like in last book you showed the means this talk was on the non-linearity by the mathematical expressions. We are capturing the non-linearity by the mathematics. So when we develop a complex network model for the epidemic, then how we there, like maybe many views can be there. I have not seen one, but how in network models we capture the non-linearity or such kind of heterogeneity. When we develop a network-based epidemiological model instead of mathematical model.
Did you hear the question, Dr. Jayaprakash?
Yes, yes, sir. First question is related to books, right? You are talking about the books.
We can,
Yeah, it can be shared.
Yes, so
you can share with us, you can share with me and I will share with you.
yes, so you can see the book of this Maya Matseva. This is a very simple book that firstly you can study if you are not studying the disease modeling, and then you can also follow some other book, Anderson and May and this
Are
disease cleaning book.
you sharing any?
Yeah, so these 4 books are very good books that you can see. So and also those books have been written with specific purpose, right? Some books you have the good modeling part, and some books you have the analysis part, and there are books those are very simple that you have to study the first, like Maya Matseva. So second question, you are talking about the network problem, right? So I do not have much idea because I did not work in network modeling.
I think
So-
Srichand will be talking about it tomorrow, and he can mention this, remember this question and address it. But go ahead, you were saying something, Dr. Tripathi, go ahead. Complete it.
No, sir, you can add on to that. Actually, I have worked on a problem. It is having the dual approach, right? One is the differential equation, and another is the network approach. But actually, we have not discussed that how actually we can have the what kind of are you formulating some kind of function in there? How you select that?
Yes, sir.
You-
How we will capture, like in mathematics, we have multiplying or dividing means non-linear saturated incidence. We are trying to capture the clear effect and base from the model or modeling. In complex network or network theory, it is also used for the modeling. So there, how do we capture these effects of the real situation?
If you allow me, I can add few things.
Yes, sir. Yes, sir.
Yeah, so first of all, I think what we are getting trained here is not about tool, it's about thinking process. So asking about, how is this method, have these things, method is always chosen from based on a research question. Okay. So that's one thing, to ask things in terms of a thinking process rather than, oh, I know this method and how does this thing work. That is first point. Second point, in network model, to answer your question, in network model, what is network model?
The
That
interaction.
you are given with the edges of a node, which is a contact. Which is a contact. So it's the weight of the edges is what influence the infection process, right? So that you can put weight different times. You were saying something, Dr. Tripathi? No, I think he's talking. So the weight of this thing decides whether a person is fear or not fear. The contact will result in the infection to what intensity that contact will result in infection. Does that make sense? So basically it is modeled. So network is something different. Network is just how people are moving and how edges and links are changing over a period of time. That has nothing to do with the infection process. But as soon as you start building
The infection
the
process.
width of the edges, skinnier width or fatter width based on the parameter on top of it, you start to describe the influence of other person on the other person. Does that make sense? What I'm saying? So it's the weight of the edges define the infection process. Now, how do you aggregate that? That could be weighted average of some sort to know the exact influence process. There are different, also in the network model, there are different ways to capture susceptible infected. It's not always captured the same way as in homogeneous population. There are separate models for that. And maybe which model you will show some things on that tomorrow. Okay. So he will talk about it and we can talk about it. But remember this is about you are building the fear. How do you build a fear? The contact will become stronger or weaker based on the fear. If two people are more fear, they will stay back at home. That means the contact is weaker. That is what it is changing. Right? Does that make sense or not? Now you can build this thing in a very non-linear way based on your reasoning, based on your assumptions, but it is just the strength of this connection which will increase or decrease. Maybe it will increase and decrease in a linear way, or it will increase and decrease in a non-linear way. So it's a functional form of it. But it is the edge weight which will change. And then if I am talking about this node and there are 10 edges connected to this node in a network, then this node is an individual, susceptible individual, then it will be a weighted average of these nodes. That is an intensity of an infection this person will get. Does that make sense? So, it's the same idea. It is not very different, except you are now adding for each edges separately rather than aggregating it one thing in a homogeneous model. In homogeneous model, you don't have the separate edges. Every person is assumed to have the same number of contacts. He's talking about data, actual data from how that is used to generate the infection process. Any more questions? There was few more questions quickly.
One simple question.
If you can be loud, we can.
Yeah. After the party, Alicia Sangha the same. You mentioned about fear function GI, right? So a few fear function you mentioned in your presentation. So I was interested in knowing how are you selecting those kind of functions in a particular form only.
The functional form. What he's saying is
Right, is in one case 1/1 plus.
really good question. Really good.
Then 1
Yes,
upon
yes.
1 plus alpha. How these functions are being selected.
Okay. Okay, you see, first of all, we want to get that what function we have to model for a particular kind of behavior, like this is the fear human behavior. So you should think firstly, the first idea should come in your mind that what kind of effect it is going to lead. Firstly, whether it is going to decrease that transmission term or it is going to add into that, right? It is going to increase that. So once you have this idea, and then you have to think about that kind of function, and at the same time you have to also think about what are the properties those should be followed by that function, so that if I construct that function, I write that function, and we put with the transmission term, because either that behavior is going to lower down the transmission or it is going to add into that. So accordingly, you have to choose that function and the property should be followed. You just see the function that we have chosen, right? Power p, and we have taken that what should be the value of p, right? And then the derivative of that function. So you have to choose that like that, okay? When you are going to take the fear coefficient 0, then it should not be there. When you are going to take the I equal to 0, then there should not be that, everything will be 0. So all the properties, derivative of that you should take care. What should be that? So derivative should be less than 0 if it is going to decrease that translation rate. So mathematically you have to observe these properties of that function, and then only you have to write that. Like in 2016, there was a paper by the Wang in Journal of Mathematical Biology, when they have actually first time modeled this function here into the model. They have described everything very properly, that what are the properties, those who will follow this function, and how it is going to reduce means the growth rate of the species. Okay, they have explained everything, and then they have chosen that function, and that should also not have any kind of similarity that you have to model like that. Otherwise it will create a problem. So in the denominator we take 1 plus alpha times e I. Why we take like this? Because when you increase the I, then this function getting lesser value, and when it is multiplied into the incidence function, then it get it down, right? Its value getting down when I is reaching. And it is saturating also, because you need the saturation level. And if there is more fear, then you are going to make it quadratic. And if you want to generalize it, then you are going to take denominator I power p, and then you address p according to the situation that you are modeling. Okay?
Yeah. So just to add what Dr. It is, we know the characteristics of certain functions already, which is very well known. We have tried various functions and we know how the shape look like, right? And some ideas we get it from social science papers, which tells it how the behavior will impact the output that you are looking for. So you basically fit that data which social scientists collected to get the shape, right shape, by using your properties, as Dr. Tripathi was mentioning. You already know the properties of some function. So you use those ideas and the real data from social scientists that they have already captured on a separate occasions, and that decides which functions to choose from. So it is a research in itself, what functions. One of the paper we did, it took us almost few months to decide on a nonlinearity. Systemizes paper, right?
Yes, sir. That could be discussed here, but yeah, sometime we will talk about that. Yeah, it has all the things very properly.
So thank you very much, Dr. Tripathi, actually, and let's give him a round of applause. Thank you, and I will message you later. Thank you, Dr. Tripathi.
Thank you so much, sir. Thank you so much.
Okay, so we will go on a lunch break, have a wonderful lunch, warm lunch in this cold weather, and then we will come back and will go into talk about MATLAB, some skill set in the MATLAB, and then we will be doing our projects, and finally I will cover some lectures on parameters. So, okay, so that's the plan. Advanced model. Yes. Okay, thank you.